PhD Endowment Chair Professor at IIIT Hyderabad. He heads the Robotics Research Center (RRC) at IIIT. He's been at IIIT for the past 21 years, and he's been with the Kohli Center for Intelligent Systems (KCIS) for the past 5 years. His primary research areas include robotic vision, autonomous navigation, and is applied to drones and indoor and outdoor robots. So Professor Madhava Krishna, as I said, he heads RRC, which is nationally renowned and it's internationally acknowledged for its contributions to robotics research. So by some rankings charts, it's ranked number one in the country. It's top 10 Asia and amongst the top 50 in the world for publications in premier robotics fora. So RRC works closely with the industry, with public organizations, defense labs, and the government of India on funded projects and research collaborations on diverse sets of areas, ranging from vision to learning to dynamics and control. So, Professor Madhav Krishna, we are privileged to have you here. So I'll hand over to you. Maybe just one little thing that it would be good if you could just clarify is whether you would like to wait to take questions at the end, or whether you're okay with people just raising their hands and asking questions on the fly.
Perhaps at the end would be better because I do not know, like if that suits you. Otherwise,
oh, absolutely.
Yeah.
Okay.
And of course, like if you also let me know if I'm exceeding the time, and then So yeah, I'm sorry for that resume. It is perhaps more pompous than it should be, but that's sometimes I do that when I'm giving these talks, when I'm invited to these companies, and if you are looking for some funding opportunities. So otherwise, I think whatever RRC is today is because of its students who have been there. I've been very fortunate to have worked with a lot of extremely bright students, and also right now we have a good set of faculty as well. So I think so you could take that as the actual thing. Of course, any rankings which we have has come because of the kind of students who have worked in RRC, and it's their research which has led to those publications, right? Yeah. Yeah, thank you, PB and Sandeep and Aditya for inviting me. And so maybe I'll start. Yeah, I think even as we speak, these things keep changing, and I'm obviously not the best in the world to talk about how AI is, doing what it is doing, right? But I'm talking from the point of view of the kind of robotics which we have been doing in the lab, and these questions keep, picking our brain as well. And so really the question is, can AI subsume classical robotics in a very rhetorical or provocative way? It could be like, should we all give up robotics and do end-to-end learning, which is to learn how to generate data and learn how to buy huge GPUs, and then have students who can train these big models. And is that the end of the day? Now, obviously, yeah. So that's, let's say that is the question which concerns everyone, and because we don't have access to the several H100s or H200s, and often we work with at most a few RTX 6400 or L40, right? So then, what is the kind of robotics one can do in that context, and can one still appear relevant or act relevant or create this illusion that we are being relevant, right? Well, that's a very utilitarian way of posing, but deeper also, what really does it mean? Whether one goes the end-to-end way or one goes the classical robotics way, right? And on the left is the wheelchair, which is actually navigating in our lab. This is the actual wheelchair, but it's perhaps rendered like a simulation in Gazebo, but that's the lab point cloud. And if you look at it, like so it's a very straightforward thing. There is a goal which has been given to the wheelchair, and the wheelchair attains the goal from its starting location, for which it has made use of a map which it has constructed before, I think with FastLeo, which is a lidar-based odometry mapping pipeline, and we stitch together and register the scene. And then we do a global relocalization with 3D BBS, and a planning which is a global planning, which is A-star, and then it navigates to the goal. It's a very short goal, short horizon, but we have moved this wheelchair across blocks, gone up on ramps and gone down ramps, and moved from one block to another and things like that, right? But this whole pipeline is a classical pipeline, which is to say, like it has a mapping or SLAM module initially, and then a relocalization module, a planning module, a collision avoidance on the fly module, and a controller as well, right? Of course, the end-to-end thing would be like, suppose I give you a bunch of images or a bunch of LiDAR data, I should, through an end-to-end pipeline, be able to get the point cloud, SLAM point cloud done, which is still not done, I think, even with foundational models, including VGGT SLAM. They don't completely do the entire map, but they can do depth and poses and things like that. And then if I query for a goal, I should be able to navigate, right? So without any of these intermediate modules coming into play, right? So this is the general idea, right? So of the classical versus the end-to-end module, right? So if you say AV 1.0, which is the way the classical stack was until say 10 years or even 5 years back, it promotes, or it's modular, which means that there are clear interfaces, clear boundaries between each module. And one advantage with that is everything is in the task space, right? The SLAM operates in the task space. It doesn't operate in the latent space. The trajectories are eventually shown in the task space. The reasoning happens either in the joint space or at most in the configuration space. But everything is something which is amenable to human to look at the output and debug, and maybe go back and change the code. And so it is very interpretable, and it is very transparent. And so that is really the advantage of this. Of course, the cons are like, so every problem, it is both a pro and the con. So the main thing which perhaps we need to remind ourselves is, in the classical stack, every time the problem is actually solved, which is every time I say do a SLAM, or the entire pipeline is solved. Like, you will estimate maybe if it is monocular SLAM, will do fundamental matrix, essential matrix, triangulation, resection, trajectory estimation, bundle adjustment. So this whole pipeline will be solved every time. So if you do trajectory planning, the model predictive controller will solve the problem for every time a query is given, which is quite unlike a deep learning or an end-to-end model, which only does a forward pass, right? I mean, the problem is not solved at inference time, mostly, by and large. The problem is only a forward pass at the inference time, whereas in the classical pipeline, the problem gets solved every time it is posed, right? And therefore, there is the challenge associated with it is, while it is indeed generalizable, because a model predictive controller for outdoor will have a very similar structure for indoor terrain. Fundamental matrix, which you estimate for indoor scenes, will be pretty much the same algorithm that works for outdoor scenes. The SLAM pipeline, the SLAM backbone will be the same. The planning backbone will be the same. But many of these methods have a lot of have many optimization, nonlinear optimization coming one after another. So all of those will have to be changed for a particular setting. And often for every time, sometimes even for every query, we may have to change either the controller gain or the optimization cost, the weights of the cost function, maybe the way the Lagrangian is posed. And like if you do a stereo reconstruction using BM or SDBM algorithms, there are a lot of parameters which are needed, which will keep changing. So these hyperparameters need to be changed every time. But the problem is generalizable in the sense it is not very it's not specific to a particular data distribution. Like it'll attempt to solve the problem irrespective of the input conditions pretty much the same way, which is both the reward as well as the curse. And of course, because it is modular, there is a lot of integration issues. For example, the perception module is unaware what the planner wants. The planning module often operates in the state space, assuming that the perception module will essentially convert the perception, the map, into a state space representation, which the planner can consume. So a lot of assumptions, and the handshake between these modules is not very convenient and not always very well done. So there can be this intermodule propagation error, right? Say from the perception to the control. So every module brings in its own error, and that can get amplified, right? So of course, the end-to-end learning framework is trying to say, like, we can do all of this in one go. So I don't need to perhaps do many of these. I mean, like if I get multimodal data, like a LiDAR camera, a GPS, everything, I can just, given this data, I should simply be able to regress to something like a steering and throttle. In case of autonomous driving condition, maybe for a quadrotor, it'll be like the thrust and accelerations or something like that, right? So, so this is the general idea. Or similarly, if I give a set of images, I should be able to reconstruct the map without worrying about the underlying, what happens under the hood, so as to speak. All right. One of the advantages, of course, of the the postmodern AI, as I call, is it has this multimodal alignment. All right. So, which is unlike the classical pipeline where the planner often operates in the state space. So you need to go an XY theta or an XY z or or a 6-off end effector pose, which is very difficult to go. So I cannot say an end effector what is the 6-off pose to which it has to reach. Right? It's very difficult for to give these goals to these methods. I would not know what is the location to which the robot has to reach, which is a few rooms away. Right? I don't have a map in my mind, or I cannot it's kind of challenging to even give the goal in a classical pipeline. But the first thing which became very easy for robotics as a consequence of the AI as we see today is this multimodal alignment. So one can now give goals in terms of, like we see here, can you find me something to wear for a space theme party and something like that, and you just have an image as an input, and maybe you also have a point cloud corresponding to it, and then the language and vision grounding module like clip or seglip, or some of them will be able to ground this NASA t-shirt as the thing that you need to wear. And if you also have the corresponding 3D point cloud of the scene, and if there is this camera to lidar extrinsics or camera to depth sensor extrinsics, then you can actually back project this NASA point cloud back into the 3D world, and you can actually navigate the robot to the NASA t-shirt, and if you have a manipulator, it can actually pick that. And so so this ability of the multimodal alignment and multimodal querying the robot has facilitated very natural, seamless human-robot interaction as a consequence of these the modern AI. Right? So, and you can also query for open set commands, like you can tell a car to take me to a roundabout, which the model may not have been trained for. And many of these models, including CLIP, and I'm sure like the more modern ones like SIGLIP, so they have an ability to understand concepts. Like, so roundabout is something which none of these models might have been trained for, but the language encoder, because it has been trained on large corpus of data, perhaps under the hood will associate roundabout to something like an intersection or like a junction, and which because they are vision and language aligned. So in the set of images which the robot has seen, or which constitutes the map, it will be able to pick up a roundabout in the scene. And if you have the lidar to camera extrinsics, or you have a good structure for motion, then it can actually understand where the roundabout is in the 3D space and navigate. So we're not actually annotating roundabouts or entrances in the Google map and then navigating it. Like it happens naturally because of this multimodal alignment. Right? And so the end-to-end models can take various shapes. So this is one thing which we have been trying to work in our lab, which is like which is a diffusion transformer, which denoises to output trajectories given inputs, which can be either in the state space or in the image space. Like in the state space, it could be a BEV layout where you have all these vehicles moving, and those representations are there in the layout, and that is passed in as a what do you call as the key and value, and the trajectory itself is like a query or the noisy trajectory, and then you can denoise it to the eventual trajectory. So this is one pipeline for these end-to-end AI, but there are many other things like, I don't know, like Pi 0.5 action chunking transformer, about which I have a very limited understanding of it. Right. Of course, there are challenges to this pipeline, which is that limited explainability and interpretability. So the black box nature obfuscates decision-making processes. Really, it is difficult if a vision language action model doesn't work. It is very difficult for the student to put his or her hand and figure out where it is, failing. Like these models, if they are too long and with several parameters, it becomes very difficult to understand and debug, right? And often these internal representations are hard to map to human understandable concepts, right? Like often there are no intermediate representations like a BEV layout map or a 3D map, or so these representations are not there, unlike in a classical formulation. right? So which means understanding and debugging becomes challenging. Deployment in low data regime is almost like impossible because most of them need very substantial training data for reliable performance. And the main thing is often, of course, with a lot of data, you can overcome the distribution bottleneck, but many of them are tied up to the kind of input distribution because the forward inference ties the model to what it has seen rather than the algorithmic reasoning, which is different from the classical pipeline, right? In the classical pipeline, irrespective of the kind of data, when I throw a question, when I throw an input to the model, it'll painstakingly or solve the problem, right? It goes through the entire process. If you do ICP, for example, right, it'll do matching, it'll do the singular value decomposition, and it'll give the last column of the the SVD matrix or the V matrix as the output, right? So it'll do this irrespective of whether the point cloud comes from snow or rock or trees or it's going to do that. It'll solve the problem. It is not centric to a particular distribution, but forward inference is actually it is like I have already fit a line, all right? So I've already learned y equal to x. I've learned the A matrix, and now if I give x, I will output y, but I'm not resolving A, right? So this is the challenge with an end-to-end pipeline. So otherwise, to overcome that, we have to constantly retrain and fine-tune as the environment evolves, right? So this is, of course, the challenge in an end-to-end deep learning situation. Of course, in robotics, specific concerns are a lot more, but I think they have been overcome with these modern vision language action models, but it's still quite different from the way vision and language transformers work. So if you have a language transformer, typically any of these LLMs, so your input is a text, your output is a text. If you do vision transformer, your inputs are pixels and outputs are some representations of the pixels, right? But if I do VLA or any of these perception to action transformer, the perception is an image or a point cloud, and the output is an action, which is there is a significant domain gap between the input and the output space, which is unlike language or vision transformer. So this domain gap problem is more challenging in a robotic setting. And unlike perhaps vision or language transformers, I mean, like you have a lot of hard constraints, right? Like collision avoidance is typically a hard constraint. And none of these learning frameworks can effectively handle a hard constraint because they all do unconstrained minimization, right? So they solve minimize g of x or minimize f of x. They don't solve minimize f of x subject to g1 of x less than something g2 of x, right? Which is the classical way the MPC or optimization problems are solved in robotics. So the constraint satisfaction is challenging. And the understanding of the underlying physics or dynamics is often missing in these end-to-end models. And there are deployment issues like control latency, like in a VLA pipeline. So if you are moving a manipulator at a certain frequency and gathering data, right? So if the actions are is passed to the joint controllers at certain frequency, and and the data is sampled at a certain frequency. But if the inference frequency is different from the way the data was sampled during training, that also creates problems. So, right, and so there are things like viewpoint variance, embodiment variance, especially, and things like that, which makes the end-to-end problem more challenging in the robotic space, unlike the language and the vision space, right? So. However, of course, like we have to keep evolving to survive this, what is thrown on us. So how have we been cooking our khichdi in RRC? Like I believe I have 15 more minutes. I do not know if I can go through all of this, but like, so these are some of these works which are kind of published, including in recent ICRA and IROS. So Crowdsurfer is a formulation where we use generative AI. By generative AI, I mean something like a variational autoencoder or a generative process of trajectory generation conditioned on certain inputs with a fine-tuning or refinement with some kind of optimal control or model predictive control. O3D Sim, where we combine LLMs for reasoning and a classical planning pipeline for navigation. Sparse localization, we use a vision language model for, or several foundational models, as a matter of fact, not specifically a VLM, but a cascading of foundational models to represent a city scale scene like Kitty in terms of sparse landmarks, and use that for navigation using a classical Monte Carlo based localization. In Lego Drive, for example, we use a vision language, a small VLM, so as to speak to take an image and a language command as an input. The VLM outputs a goal, which a planner optimizes for in a differentiable manner. So this is what we do in Lego Drive. EDMP is a diffusion policy, so as to speak, with guidance. Guidance comes from something like a CHOMP style collision avoidance classifier. So the collision avoidance is directly borrowed from the CHOMP, which is a classical motion planning pipeline. And DACDIF is a recent paper which has been presented in this ICRA, which for dual arm grasping, where once again we use diffusion plus guidance in the form of classifiers which detect collision, which look for force closure to generate dual arm grasp. Right. So this is the way, like where we are trying to emphasize that, especially if you do not have access to several H100, H200, and if we do not also have the expertise to train these models, like it's not straightforward. But we can use these, we can still solve very interesting problems by combining inference on these models with classical optimization or classical robotics techniques, and solve problems which otherwise was very difficult to solve in the purely classical domain. Right? So, just a couple of seconds as I drink some water. So the smart wheelchair is a project which we have been working on a few years from now. So it is supposedly a translational project or deployment. So we have deployed it in some malls and in some, not within the airport, but in complexes just outside the Hyderabad airport and all. So it has a bunch of classical plus modern AI stack. So it uses a classical model predictive control with cross entropy minimization for trajectory optimization. It has a lidar to camera extrinsics as well, and traditional AI, like A-star like planner for the global planning. So the mapping, planning, navigation, all is classical. But what it can also do is it can take in language command. So it can take a very natural language command given as a text as an input. It can also convert scenes to a multimodal trajectory distribution through flow matching or VAE kind of process. So if you give an input scene as a BEV, it can generate multimodal trajectories on that. And it can convert a complex language command to goal sequences. So this is a combination of, it's a khichdi or really of a bunch of things. On the deployment, of course, we still continue the classical stack, but a lot of these things are also in play. So I'm not going into the details, but this is like, for example, I say I need to put some hardware away first and then store some books and keep clothes. And so the moment we give the command, so it understands the table as hardware to put, right? So so this is what we say like concept learning. So it has kind of understood this concept of hardware. It has mapped it to a table, and then it has also sequenced it. Like the LLM then passes this and identifies, like it says, like you need to put the hardware first, right? So do this first and then keep the clock. So the LLM passes this query, and then we have this foundational model like CLIP, which will look at all the images which constitute the map, and it will kind of figure out a table as a place to keep the hardware. And because we have the lidar to camera extrinsic, so in principle, every pixel in the image can be back projected to the 3D lidar point, and then it finds out the table as a location to keep the book. And of course, we don't have a manipulator here, but so the wheelchair navigates autonomously through the classical stack to reach the table, and then it navigates autonomously to reach the cupboard as a place clothes can be kept. Right? So this is what I call as a reasonable mixing of both the modern AI and the classical navigation stack. And what is interesting is, so it is very difficult for any user to say what is the location of the table, right? I cannot do this XYZ or location on the table for the end effector or a mobile manipulator from its starting position. I mean, it's pretty challenging for any user to say that, right? I mean, it's, if you think about it. But with this pipeline now, this very seamless interaction with the robot is now possible. Like you can just interact with the robot in a very natural way, right? And in Crowdsurfer, what we say is we do something which like a human, if you're a human being, if you just give them a scene, right? Like when I look at a scene or when I look at the environment in front of me, I can kind of map this environment into multimodal trajectories. I can immediately think of in my mind, well, I can move around this table this way. I can also move around this table the other way. So there is this mapping from the input space to the space of multimodal trajectories, which happens in the human mind through whatever process, right? So in this crowd surfer, we used a vector quantized variational autoencoder. Basically, we learned the distribution of trajectories through both simulation and real data. And then we quantize these trajectories through bins, through this vector quantized. And given an input scene, so we have what we call as a pixel CNN, which learns a distribution over the bins. So it learns a distribution over the vector quantized bins. And then it will sample from each of the bin in proportional to the distribution corresponding to the input scene. And then through this process, we will generate multimodal trajectory which based on the input scene. The input scene, of course, is not the image itself, but it's image in the form of the occupancy map or the BEV layout, right? And therefore, you kind of get these very diverse set of trajectories. And then we choose one of the trajectories, through some scoring function, and then we also optimize for this trajectory through a model predictive controller. So as a matter of fact, we can actually do a batch optimization on these multiple trajectories. And so this was implemented on the wheelchair. And so we are able to run this on an onboard laptop. As a matter of fact, we managed to also run it on an onboard Jackson Orin, I think. So yeah, right. So and this is on the Husky outdoor. So it is the entire generative AI plus the classical MPC stack which runs. And recently, let me see if I can show this. Now, through this, this diffusion pipeline,
Silica,
so we managed
a joint
to
glass segmentation and
do this glass segmentation, right? So, for example, for any of these mobile robots or drones, so if I have highly transparent glass structures, both the lidar and the RGBD sensor, unless you have a radar, right? So they will simply see through the glass, and it is very difficult to navigate in highly glass environments. So this was something which we figured out when we took this wheelchair to deploy in a mall, and in the mall, everything around us is glass, so mapping becomes very challenging, relocalization becomes challenging, navigation becomes challenging. So we wanted to figure out a way for doing two things, to segment glass in a scene and also get depth to the glass. All right.
estimation
and
model.
the way we do, I'm not showing the method here because the video is not showing the pipeline. But the pipeline is we learn the latent space through what I call as a latent space flipping. So basically at inference time, if you query the unit diffuser with the latent space of the image that the robot is seeing, along with a clip conditioning which says whether you want the segmentation of glass or the depth for the glass. So what the model or the unit will output is the latent space corresponding to the segmentation output or the depth output of the glass structures corresponding to the input latent space, right? So this is what the unit does. Of course, the input scene is converted to a latent space through a image encoder, right? And then using clip, we can switch to either a segmentation output or a depth output. So the denoising happens in the latent space, and then there's a decoder which converts that back to the actual depth and segmentation output, right? So this is
standard depth cameras fail to perceive glass.
So here, the wheelchair kind of is navigating, and it'll actually, if you don't, here it is manually stopped, I think. But then we say through our pipeline, we actually manage
forcing us to manually stop the robot to prevent collisions. Silica solves this by predicting accurate metric depth, which is updated in the cost map, allowing our MPPI planner to safely route around the glass pane. In this next scene, the standard depth camera again fails to detect the glass, requiring an early manual stop. Silica, however, consistently estimates metric depth to glass, enabling safe navigation through the open glass door, showing our model's robustness. Here for mapping, standard depth sensors with RTAB map fail to register glass in both 2D and 3D maps. But with Silica, the glass surfaces are mapped accurately, highlighting our model's strong zero-shot performance. Finally, here are some Silica predictions captured on phones and other cameras in various hard scenes, showing its generalizability. Thank you.
Here, once again,
Silica, a joint glass segment.
The point which is being hammered out, so as to speak, is this combination of what I call as the classical navigation in presence of glass, but a foundational model like the unit, or almost, I think it's a stable diffusion unit, which has been repurposed to both segment glass and get depth to it. And I think at this point we also have an onboard implementation on a Jetson Orin through an equivalent, something equivalent to a TensorRT, not exactly that. So this is a wheelchair here. However, when we want to deploy, so we in a actual environment. So this was a deployment in our R&D showcase last year, and that was done with maybe it's not here, maybe the wrong video. So yeah, it's. So in these kind of slightly uncontrolled deployment scenarios, we still are. It's fairly classical. Of course, the foundational AI can be integrated, but because this runs on a Jetson Orin, it's not possible to do these language command and all that kind of pipeline on a Jetson Nano or a Jetson Orin board. But right now we are looking at those possibilities as well. Right? So okay. Yeah, Sujit, how much do I need to stop? Or like?
I think Professor Madhava Krishna can go on another 5-6 minutes, and then we can stop.
Yeah, thank you. Thanks. This is another, the same wine in a more modern bottle, which is what we call as the flow matching. Flow matching is another generative AI framework for learning. So using optimal transport, the flow process can learn to move from one distribution to another. So basically, starting or sampling from pure noise data. So we learn the distribution of trajectories. And once again, that is conditioned on the input representation, which is like the BEV layout. And and we kind of also got this implemented on the P3DX. We were finding it challenging to get it done on the wheelchair for some reason. Right? So I hope I hope to see, like, this is the multimodal trajectory distribution corresponding to a scene which you get. Right? So for any input scene, you will get a multimodal trajectory as the output, and then you can use a batch MPC to optimize for these trajectories in a batch, and then also choose the best trajectory to navigate. Similar things for autonomous driving. So here, this is something which we did just at the advent of GPT 3.5 and CLIP. So we here query for regions like roundabout or football field, and the vehicle will reach to this destination. So for example, here we say, take the car to the roundabout or take the car to the football field. And because these CLIP vision language multimodal aligned encoders are trained on concepts, so though it may not understand, it will associate the language encoder, I think, under the hood associates football field to a large open area, and it will give the encoding corresponding to a large open area. And because it is also vision aligned, so in the image, if you see a large open area like a field, like a football field, in this particular case it was a ground, it will navigate. And if you all have the 3D, corresponding to that location, because in the map, I can then localize the football field and navigate to this open segment. Right? So basically now I can say, take the car to the roundabout, as we say in the right, or take the call to the football field, as we say on the left side, football field. And that gets activated in the LiDAR map. And then you can actually go to the football field autonomously. Similar thing. So we use this for a similar pipeline, but now through a combination of Llama 3.2, grounded Dino, and SAM. So we, given a sequence of images of a kitty scene, we instead of building a dense 3D map, using these foundational models, we register landmarks such as like buildings, like what you call the signboards and things like that. So basically, we tell the llama analyze the image and describe what you see, suggest what potential static landmarks you see that can be used for localization tasks in an autonomous driving setting. Do not consider dynamic objects. And then I think llama says tree trunk, building, facade, and all that. And with this caption, we use, I think, grounded Dino and SAM to get the bounding boxes for these landmarks over the video sequence, such as this. And because we have the LiDAR to camera extrinsics, we can back project this, the corresponding region into 3D. Then we can get a kind of a landmark representation. And then we can sparsify it further by taking the centroid of the landmark and then just use that. So what we showed here was, instead of a 4 million point cloud, which is what one will get if I do Lego Loam or Loam or like Leo SAM, I will have a 4 million point cloud to relocalize myself in them. But with this assortment of foundational models, we reduced this 4 million point cloud to just 4,000 centroid points. And then we showed during inference, I again have the same set of query, and then I can recognize that in my scene. And then I can map what I'm seeing to what I've already seen before, and then I can relocalize myself without any prior. So we managed to relocalize on the scene with this sparse set of landmarks through a Monte Carlo method. And then we use the traditional classical Monte Carlo to kind of keep propagating with odometry and some kind of an optimization, kind of a small laped optimization, like a post-graph optimization over landmarks though. And we showed a very successful localization run on these KT scene without the need for all these very dense 3D maps. All right, so this is another example of using foundational models with a classical mapping and relocalization pipeline. So we call this sparse lock. And Lego Drive is another very interesting problem where we convert a vision language model to a goal region and then use a differentiable planner to update the goal such that the planner can reach that location. So for example, here, I think switch to the left lane. And so switch to the left lane is the language command, but that is converted to a goal region. And the planner navigates to the goal, but in an end-to-end way. So basically, we have a kind of a clip vision encoder and clip language encoder. And this is, I think, what they call as the ATTP transformer, which operates on these tokens. And then there is a decoder, which decodes this into a mask and a predicted goal location. And this goes as an input to a differentiable trajectory planner. And the planner has a self-supervised loss of whether one can reach the goal. I mean, if the goal output is, normally these decoders may not give the goal in a location that is very comfortable for the planner to reach. Right, so this is the problem in a classical modular pipeline. The perception stack may give goals or may give a map which cannot be directly consumed by the planner. So, but here what we say is because we have a self-supervised loss both on goal reaching and the trajectory quality itself. So this loss will propagate back to the decoder, and the decoder will keep updating the goal in a way the planner can reach. So this is a very nice marriage of the modern AI with a classical planner to accomplish end-to-end navigation. And so here the part behind the bike.
Professor Madhava Krishna, just maybe we can end.
So the green goal was actually the wrong goal. The red is the corrected goal through the differentiable planner propagating back to the decoder, and the decoder updating the goals. So of course, at inference time, we just do a forward pass on the decoder, and the decoder outputs the goal, and the planner plans the trajectory. And yeah, so with this I will stop. I'm not showing the other things which we have done, combining or cooking the khichdi this way, as I say. Yeah, if there are questions, should I look at the chat box, Sujit? Or
no? Thanks, Madhav. I think it is, as usual, a great talk with a lot of insights for students. I think we'll just take the students, like the questions in the chat box, or if anybody is interested to directly ask, they can switch on their mics and then
email me also. Often you see like if the students who are doing, I may not be on top of all of this, so if I do not answer straight away, if you can email me, I can also figure out a way to answer.
Yeah. Any questions from audience? Okay, Sandeep wants to ask.
Awesome.
Sure. I have a quick question. So here we are trying to balance between end-to-end or some kind of learning with like controls, right? Like fundamental controls. So do you have a suggestion on like how do you actually decide, like in a given problem, how do I decide like what should go with learning and what, like how do you do that?
Okay. So normally what we have seen is most of these learning models, at least the kind which we use, unless you use direct VLA, right? Suppose I use diffusion policy or flow matching. What we see is the output trajectories or actions typically do not satisfy the constraint. Typically means like you will never guarantee, you can't guarantee it will avoid obstacles. Okay. So therefore we naturally invoke a classical pipeline there. Now the question is whether I just do it at inference time. There are various ways of marrying the two. One straightforward way is you have the AI module which outputs the actions or trajectories, and then if the trajectory is not really navigable, I use that as an initialization to an MPC, and I do an MPC on top of it. But now normally what people do is they do this inference time optimization on diffusion. So I send the trajectory or the action space to a classifier guidance, right? So the classifier says whether there is a collision or not. So we use the CHOMP collision detection module for a trajectory which we generated for using diffusion for a 7-DOF manipulator. And then what we do is, because it detects a collision, so we take the gradient of the classifier. So we can, because it's a classifier, and then you can take the gradient of the classifier output with respect to the joint trajectory input. And then we kind of, what we say is we shift, there's this standard process in guidance and diffusion policy. The gradient will be added to the noise, which is getting denoised, and then that kind of shifts the distribution at inference time, and then we this kind of works sometimes. So basically, it's not like we per se go with a design, but what we see is like having this the classical pipeline also integrated makes more sense, or it does a better job. And that's what we have seen for at least the planning frameworks. For mapping our relocalization, like it is like for this, for example, this sparse lock was something which it came to us naturally, okay, we can use these foundational models to be able to segment a lot of landmarks, and then we can use a classical pipeline to relocalize the, because that's much faster and more real time than if I use something like a VGGT or something for relocalization. So basically, I think at least if you have low compute, I think that any diffusion policy, like diffusion policy 3 or even the 3D flow actors and all that, so they do not always satisfy the hard constraints. So having a classical refinement over it is seems beneficial, right? So that's what we have seen.
Okay, thanks.
There's one question from the Karthikeyan Ganesh Shankar. I wanted to hear your thoughts on generalizing E2E navigation across different robot variants, soft, wheeled manipulators, etc.
That I do not know. Like, we have not been very successful on. We tried to use pi, trying to transfer pi zero from, but we did it in a very different way. So, so trying to do this embodiment transfer between Franca Panda to Exxon 7, and we were not very we were not very successful with that, and that's something which we have not done. So I cannot answer on that. Having said that, like we have generated grasps using, but then they are agnostic to the manipulators. So so this we do this decoupled way. So we generate grasps through a diffusion model, and as a matter of fact, bimanual grasp through diffusion models on a point cloud, and those grasps can be executed by any embodiment. It could be a dual arm Panda or a dual arm Exxon 7. As a matter of fact, we showed that those grasps, we do the simple real transfer of those grasps on a real point cloud, and then we picked up something like a quad rotor with one Exxon 6 and one Exxon 7 together, and things like that. But then that's all decoupled. So the only way we have done cross embodiment is this classical way. You get the grasp through a generative AI pipeline, and then use inverse kinematics to navigate to the grasp on different embodiments. So as a matter of fact, we show like the left arm is an Exxon 6 and the right arm is an Exxon 7. Yeah. So that's not answering your question, but that's the way we do.
Thanks, Madhava. So, Madhava, one question. So, is there going to be or at least like, are you pushing towards some kind of an robotics foundation model in India?
That I don't know. I told no, I've become old, Baba. No, I don't know, like robotics foundation model in the sense whether we should work together for, is that what you're asking? Or
no, is there any efforts already thinking about that directions? That is the first question. And then later on other parts will come.
I don't know, Sushir or somebody in ISC, I don't know whether they are looking at it, RL and all. I'm not.
There's one also from Laksha, like Deepan, and we had submitted for India AI. So
I see.
But it's mostly on locomotion. Correct.
Yeah. So this is like a vision language action model, or what is? I mean, like,
yeah. So vision language action with ALMs and VLS. Yeah.
Oh, this is funded by India AI.
No, it's not funded. We have submitted.
Oh, okay, the India. Oh, that way. Yeah. So we are we have an India AI grant on, not on the action, but vision language geometry foundational model. So the idea is basically to be able to handle geometry queries, like can I navigate between these two cars on the India driving data set. But that's not on robotic foundational model and VLG, but we don't know, like it's kind of, it has been granted, but we have not got the GPUs yet.
Okay.
But it's something local, I do not know, like maybe Sandeep will have a better idea on things, maybe. But maybe Sandeep, what is your own take on this? Like, is the end-to-end the way forward, or what is your thought?
Yeah, I don't agree with end-to-end, but then also like the way things are going towards, it looks like that's what we are all going towards it. But then I don't want to work on end-to-end, but then am I forced to work on it? Is another thing.
No, I mean, I also don't know. Like, but what I mean, maybe if you get tactile input and all for manipulators, then maybe. But
I don't know what like for me again, foundation model is again a new term just used for generalizable learning, right? Like people have been working on generalizable learning anyways.
Right.
So I don't see calling it another name as foundation model, but then basically like, but then more like using the same model for robotics. If I say like foundation model for robotics, and then I can't imagine it working on different modes of robots, like either a ground vehicle with an underwater vehicle with, and being able to transfer the models between those. I don't
that's not
see that happening.
Easy. And I mean, like what is also worrying, or I do not know, right? So for example, like if you do very classical robotics, right? So with say a 7-DOF manipulator, there are things like null space control, right? Like say, for example, you do visual servoing with a 7-DOF manipulator.
Yeah.
So you have the primary task, which is goal reaching, right? And then the secondary task is done in the null space. So you do this q dot equal to j pseudo inverse e dot, and then that q dot you solve for servoing to a particular image configuration through a classical visual servoing. And because you also have the null space, what you can do is you can do the avoidance. You can maneuver the avoidance in the null space, and that will not change the end effect, right? So I mean, like, so these kind of formulations, I do not know when you do end-to-end what happens to the null space constraint. Is it like, are you actually solving it in this way, or like a lot of these things get submerged under the table, or like you do a classical Euler-Lagrange dynamical solution. Now I do not know what happens when I do a E to E framework. Am I looking at the mass matrix, inertia matrix, or all that is not needed? So when I do this cross embodiment, there is a lot of dynamics, right, coming into play. And so I think, like, my hunch is like if people or students are still good with those dynamical systems, at least they may be able to reduce the data set or the training time or even the GPU requirements, perhaps if you use this physics-inspired neural networks and things like that.
I think that's the only hope, like physics-inspired learning or physics-based RL kind of things, which are basically like informed with physics systems, and those would be also easier to move from one system to the other. I feel that's what we can look into.
I mean, the other concern I have is like if we surrender the thought process to even like people use this cloud for doing a lot of coding. So now students are not able to understand that the the cloud, what kind of coordinate transform is it using? Is it using a left-handed coordinate system, right-handed coordinate system? So things don't work, and people don't know why it is not working because they have not written the code. And
we have many students here, so maybe we can get their inputs too. Like, what do they think? If anyone wants to talk.
Nobody wants to talk.
I can be very tongue-in-cheek and say we should be very afraid of students now.
Yeah, I mean, a few years, I was talking to a colleague of mine at IITB, and we actually thought a great career option for the two of us was to start breeding horses, given what our students are likely to build in the next 10, 15 years. So, but okay, anyhow, sorry, I'll take that comment back.
Thanks.
Any other questions? I don't see any questions in the chat.
Can I ask a quick question here?
Yeah.
I'll keep it short. So just following up, by the way, on this theme of end-to-end learning versus trying to build a picture of the dynamics. See, one challenge that I see with end-to-end learning is that you're building the entire algorithm on a single vehicle. Now imagine a setup where you're purchasing vehicles, like let's say you buy the Jackal or any of those platforms off the shelf. I mean, as you mentioned with the manipulator, they already have the equivalent of an inverse kinematics built on board. So with these vehicles, they are generally good at, let's say, going from one endpoint to another. So the question is, what is the value of overwriting some of those with this kind of an entire end-to-end kind of a pipeline? I mean, that's one thing I've generally not like, and I'm not asking this as a challenge, but more as a question of, if we had to justify doing it, what would that justification be?
Oh, I see. Okay, I think I think when at least on, I do not know, like in the autonomous driving or mobile robotic space, the idea perhaps is not to override the underlying controller, right? I mean, like even in manipulator, the vision language action models will output maybe joint rates or joint locations is what pi 0.5. Oh, okay. But you still use the controller to navigate to that. All that it is doing is, previously, let's say I would do it in a very classical way, right? So I have to have an obstacle avoidance constraint through an MPC, which is very challenging, like for a 7-DoF arm interacting with a workspace. If you think of the avoidance constraint, like it's kind of becomes very challenging to write the constraint and have a nonlinear solver solve for it. People do RRT connect and sample a lot of these controls and then find out. Now, what people are saying is, I give a lot of data and then I give this environment, then I should be able to output the a chunk of actions. But the action chunks are finally also like commanded. It's the controller is not overwritten. So in case of your Jackal, also your Jackal's underlying controller or Husky or P3DS or a wheelchair, that controller will not be bypassed.
Okay.
It is only that you can say that the action models will give us sequence of waypoints to navigate, or maybe a set of velocities. But the velocity, you still have a PID controller to track the velocity.
Okay.
Yeah, so just a small thing to add. I think it also kind of gives a common platform, like a framework, right, for all the different platforms that you would want to integrate with. Like if we have a good framework, that's what I'm saying. Like if you have that.
Yeah, that's true. And actually, so part of that formalism in aerospace, at least, it kind of exists because, like the way we do control design typically is you stabilize the vehicle, then you manage the guidance, which is the velocity and, where it's flying. And then on top of it, you have the navigation stack, which is where do you route the vehicle. And if you look at that entire stack logically, this is exactly what goes into any ground vehicle in general. And when you think of where should the vehicle go, or where should any mechanical object go, it really comes to choosing the correct waypoint. Correct. Now the challenge with choosing a waypoint is collision avoidance. So really the question then becomes: are you doing collision avoidance and waypoint selection as an end-to-end, or are you happy to recommend a waypoint and let more classical collision avoidance methods work with the rest of the stack?
Yeah, the latter is what we have been doing, but I think the former is what the VLA guys are advocating. They want to kind of roll out trajectories. They just want to roll out the action velocity, over a time horizon.
Yeah.
The MPC is what they want to learn end to end. I don't know. Like, see, the certain advantages which the AI brings to the table is the multimodality, right? So you can, because this generative AI, you can sample a trajectory distribution more easily, which is not possible in a classical thing. I will do only one trajectory as an output, but now I can sample multiple trajectories through attribution more. Number two, it also allows for this language alignment, right? So, for example, if I say, can you move around the far ahead of you from the left? So this, the ability to give a trajectory corresponding to this, which is kind of difficult in a classical context. But I think it is true that none of these models can guarantee the hard constraint satisfaction. That's what we say.
So would that be the next level to look at, say, guarantees as part of these learning ways?
Yeah, perhaps. Yeah, I think using some kind of like there are these convex optimization neural network, or they use these differentiable layers in networks and do things. So that's certainly one thing.
Okay, Madhav, I think. Okay, there is Samit Pradhan. Yeah, you can go ahead. This is the last question.
Thank you. So regarding multimodality and in general cross embodiments, I had one query. So while a lot of these models like Pi 0, 0.5 and all, they claim that their models generalize very well across cross embodiments and so on. How has been your experience when you try to, let's say, take checkpoints from one of these and try to apply to something that that has a different embodiment? Because we've been internally trying to let's say we have started with OpenVLA and we've been exploring their checkpoints. However, the deeper we start digging into these let's say the data set accompaniment, the calibrations, more we are realizing that they kind of are either overtrained on certain embodiments or environments, whereas they don't really generalize so well. So is it a problem? Where does the problem lie? Is it in the data set training or the architecture itself?
Yeah, I think, as I said, we were not successful, but I can put you in touch with a student of mine who cut his teeth with research in our lab, RRC. Right now, he is joining as an assistant professor. He's starting the robotics program in Johns Hopkins. Okay. So he was at Meta. He did his PhD in Mila, then a postdoc at MIT AI lab, and was with Meta, then now he's in TRI, Toyota Research Institute before. So Krishnamurthy, he has done a lot of Pi 0 fine tuning, but there is a lot of process to be followed, which is what we figured out. But we were not successful because we were doing it the kind of a little bit hard way. We could not actually do this cross embodiment. We could not learn Pi 0, I don't know about Pi 0.5 on our exam 7 based on the checkpoints for Panda. But we figured out we were doing a lot of things which were not correct, and there is a whole recipe of even doing this fine tuning. So if you can send me an email, I can put you in touch with him and see if he can be of help. There was another startup. Perhaps you are from a startup, or I do not know.
Yeah, I am from a startup called Nico.
I see. There was one more startup which he helped. Like they also approached me, and then I put them in touch. But what we have been doing is we have not done this VLA style. We use diffusion or flow matching, and we do this bottom up. So we generate a lot of trajectories. We add noise to the trajectories. We use flow matching to denoise from sample distribution to trajectory distribution, but that is on a restricted environment. It's not like we are not claiming that it's going to work in Mars and Jupiter and Neptune and all that. In the lab setting or in the environment where we work, we have done that to reasonable, I can show because, so we have some papers called EDMP, which is ensemble of diffusion portion policies. You can look at it. And so we did the diffusion in the polynomial space as well. So we call that, I think, generalized polynomial diffusion. So that we were actually also able to do it on Robotica. But it's not like we are not claiming any cross embodiment. But the whole, the advantage is that we know the diffusion policy is ours. Like, the weights are being trained by us and it runs this by us.
One more last question. So maybe we can also take this offline. So I stay in Hyderabad, close to IIIT as well. So would it be possible to visit your lab sometime? Maybe we can discuss a little more.
I'm here typically. Of course, anytime. Like Saturdays or come.
I'll drop you an email then.
Yeah, sure.
Thank you.
Thank you.
Okay. Let's all thank Professor Madhava Krishna once again for a great talk, and thanks for taking time and joining us.
Yeah, thanks, Sandeep. Thanks, Gigi and Aditya. And sure. Thanks.
Thank you.
Thank you, everyone.
Thanks. Yeah, thank you. Thanks a lot.
Thank you all, and see you guys next week.